Differential coding part 2. Now let us explain and see how we can achieve the correct bit pulse of information at the receiving end. The differential coding and decoding scheme has been discussed in part 1. In this part, we will discuss the encoding and decoding techniques in details. The encoding circuit is shown in this figure. Here, let us consider the information or the message bit train as dk and the output bit train as ek. Now the feedback delayed bit train as ek minus 1, which is XORed with the information bit train dk. Therefore, here the output bit train ek equal to dk exclusive or ek minus 1. The arithmetic rules for the modulo 2 adder is given by 0 exclusive or 0, that is equal to 0, 0 exclusive or 1, that is equal to 1, 1 exclusive or 0, that is equal to 1, 1 exclusive or 1, that is equal to 0. Table 1 shows what we are getting out of encoding. Here dk is the input data message or the input data stream. The initial state is ek minus 1 and the output data stream will be dk exclusive or ek minus 1. The encoding circuit has a reference bit. It may be 0 or 1. It doesn't matter. Here we will consider reference bit as 1, the initial state as 0. So ek will be 1 exclusive or 0, that is 1. Now let us consider the input message or data stream as 0110011. Now here the initial state will be 1, so ek will be 0 exclusive or 1, that is 1. Next, again the initial state will be 1, so the ek will be 1 exclusive or 1, that is 0. The next initial state is 0, so ek will be 1 exclusive or 0, that is 1. Next initial state will be 1, so the ek will be 1. Next initial state ek minus 1, again 1, so the ek will be 1. And next the initial state ek minus 1 again will be 1 and the ek will be 1 exclusive or 1, that is 0. Next the initial state will be 0 and ek will be 1 exclusive or 0, that is 1. Now let us see the decoding technique. The decoding process reverses the encoding. The decoding circuit is shown below. The incoming bits are added to create the input data sequence dk, and this dk here will be ek exclusive or ek minus 1. Now there are two possibilities. Number 1, the received sequence is not reversed, and number 2, that the received sequence is reversed. Now let's see how the circuit deals with each of these possibilities. The table 2 shows what we are getting because of decoding process when the received sequence is not reversed. Here the channel data is ek, the initial state will be ek minus 1 and the data stream received at the output, that is dk, which is ek exclusive or ek minus 1. Here also we consider the reference bit as 1, the initial state as 0. So dk will be 1 exclusive or 0, that is 1. And here ek that we will get from table 1 as 1 0 1 1 1 0 1. Now the next initial state will be here 1, and when this 1 is XOR with this 1, we get dk as 0, and the next initial state here will be 1 and dk will be 1, and next initial state for this will be 0. So the dk will be 1 exclusive or 0, that is 1, and next initial state will be again 1 and dk will be 0. Next one will be 1, dk will be 0, and next it is 1 and dk will be 0 exclusive or 1, that is 1, and the next initial state will be 0. So dk will be 1 exclusive or 0, that is 1. Now let us consider the case when the inversion takes place. If ek changes to ek bar and ek minus 1 changes to ek minus 1 bar, then we have dk is equal to ek bar exclusive or ek minus 1 bar. Now let's see what happens in table 3. So table 3 is the representation of the decoding output with sequence inversion. Here the channel data ek bar and the initial state will be ek minus 1 bar, and the data stream received at the output will be dk, that will be ek bar XOR ek minus 1 bar. Now considering table 2, here first bit for the channel data will be 0 and initial state will be 1. So dk will be 0 exclusive or 1, that is 1. Now from table 1 or considering table 2, the channel data will be inverted, so it will be 0 1 0 0 0 1 0. Here the initial state for this will be 0, so dq will be 0. Here the initial state will be again 0, the dq will be 1 exclusive or 0, that is 1, and for this the initial state will be 1 and dq will be 1. For this the initial state is 0, dk equal to 0. For this initial state is again 0, dk will be 0. Here the initial state is 0, so dk will be 1, and here the initial state will be 1 and dk will be 1. The table 3 shows the message received, that is dk is still without any bit error. In either case, by using the magic of binary numbers, we are able to get the original bit sequence back. Now let us see the table 1, 2 and 3 at a glance. Here the input data stream dk initial state ek minus 1 and ek will be dk exclusive or ek minus 1 as shown in table 1, and difference bit is considered as 1 and initial state 0, so dk equal to 1. Here it is our bit stream or the initial data stream. Now we get the ek, the output message stream after encoding. So the ek that we get after encoding is this, and our input data was dk. Now consider the decoding without any bit inversion. In that case, table 2, as we have already discussed earlier, it is clear from this. These are the output stream, message stream that we received from the decoder circuit, and it is clear that dk, the input message signal, and the message signal received after decoding is the same. Now consider the table 3, when the bit inversion takes place during transmission. Then what happens? It is clear from table 3. The reference bit here ek in comparison to table 2 will be ek bar. So reference bit 1 will be inverted, that will be 0, and initial state again it will be inverted. So for instead of 0 it will be 1, as we discussed earlier also. So here dk will be 1, and here the channel data that was ek earlier, but it has been inverted, so ek will be here ek bar, so we will get the inverted data here in comparison to table 2 or table 1 also. So here the initial state will be this, and so the output stream that we will get, it is clear from this table, already we have discussed earlier. Now it is clear that when the sequence inversion takes place, then also we receive the same data at the output. So we may conclude, using differential coding technique, always we get the right data stream at the output. Now we can verify this using Boolean algebra also. So for more details, we have to continue to differential coding part 3. Thank you.